Good morning, everyone. Today we're going to continue our discussion on time series using Arima. So far, what we have done was to come up with a model for our log returns of Apple, uh, an AR1 model. Before we go there, let's just quickly review what we have learned so far. What we did was to download data from Yahoo Finance using the get symbols function. Okay, sorry. Let me scroll first. So we downloaded the Apple data from January 1, 2015 to uh, January 1, 2025. And then we got the closing price. Okay. And then with this closing price, we got the returns because what we are modeling is the returns. Okay. So where's our returns? I'm sorry if I keep on scrolling. Apple close. Okay. And Apple close data. Was that our returns? Wait, I'm sorry, class. So this is just the closing price. And then what we did was we said that to get the log returns, we have to, okay, where is that? Here, Apple log returns, which is we get the log and then the difference of our data, Apple close. So make sure that it's already existing in your environment. It's already in my environment here, Apple log returns. Okay, I will not run that again. And what we did was to make sure that we omitted the first row, which will be an NA because it has no prior value. So when you get the difference of that difference compared to the previous value, since there's no previous value, then it will return an NA value. So we had to omit it or delete it. Okay. So we said that part of the process of determining the Arima model is to make sure that the time series is stationary. Okay, so we can do this using the augmented Dickey-Fuller test. Let me plot first the Apple log. Okay, and you can see here that seems to me that the time series is stationary, no trend. Okay, constant mean and constant. For the constant variance, that might be subject for discussion, but generally, there's no fanning out of your time series of your returns, okay, or fanning in of your time series. So we tested that statistically. We use the ADF, augmented Dickey-Fuller dot test, okay, and we said that the null hypothesis here is that the time series is stationary. Okay. See, sorry, the time series has a unit root, therefore it's not stationary. The alternative hypothesis is that it is stationary. And the p-value is 0.01. So this is much lower than 0.05. Therefore, we reject the null hypothesis of non-stationarity. Indeed, the time series is stationary. So once we have determined that the time series is stationary, what we do is we plot the ACF and the PACF. The purpose of doing the ACF and the PACF plots is that from there, you'll be able to determine if the series is an AR process or an MA process. So for example, if you take a look at the ACF autocorrelation function, you'll be able to determine if the time series has an MA component. So what do we mean by this? So let's say this is your ACF and this is your Bartlett bands. Okay, these are the dotted lines that you see in your ACF. And if you see that there's a significant spike, let's say this is log 1, and then this is, let's say, log 2, and no more here. So this is your ACF. If you have a significant lag, okay, this is significant because it's outside the confidence interval here. If you have a significant lag, let's say this is, let's say 0.7, okay. Let's say this is 0.3, sample only. The height of this is 0.7, the height of this is 0.3, and this is the ACF. This is indicative that you have an MA process. An MA process, moving average process, shows that you have significant spikes at certain lags, okay? And then the rest are no more, not any more significant. And your PACF also looks like this. Your PACF looks like a quick decline there. So your PACF might be looking like this. Okay. So if your ACF looks like there's a significant spike at lag 1 or lag 2 or lag 3, and then you have here a exponential decay, your plot is looking like this one. These are your spikes there. Then this could indicate that this is an MA process. On the other hand, if this was reversed, okay, let's say the significant spikes is at the PACF. So I'll say this is PACF, and then this is your ACF. So the situation was reversed. You have significant spikes at, let's say, at lag 1 in the PACF, and then your ACF looks like a decaying, quick decay. Then this is indicative that this is an AR process. Okay, if there are significant lags at the PACF, then this is indicative that it's an AR process. However, if both ACF and PACF show significant spikes at certain lags, okay, then that might indicate that it's an ARMA process, an ARMA process. Okay, so you had to be trained before to really try to guess if it was an ACF, if it was an AR process or an MA process, and guessing will not oftentimes not really bring accurate results. So what will happen is that you will have to do some several guesses and come up with a model, several models. Okay, so maybe it's best to, why don't we do this? I'm sorry, I wasn't able to get the example. Okay, maybe let's Google this, class. Let's see, ACF and PACF plots for AR and MA processes. Let's see. Let's have an example so that it becomes more clear to you. Okay, let's maybe here. Okay, let's see. This is from Duke University. Let's see if they have here some illustrations. Okay. Okay, there you go, class. Okay, not here. All right. This is your ACF. Okay, this is your PACF. Not so clear. Okay. Okay, let's change. Let's find another one. I'm sorry, I was able to, maybe we can find it in the images here somewhere. All right, maybe this one. So we have here some images. Okay, let's see this one. Okay, so this is, all right. AR and MA, let's have them. I'm sorry, I can't find an example right now. Okay. This is not uh, a good example. Okay, but I hope class that you try to find an example. We have several plots here, but they're not so much explained. Okay. This is the exponential decay I was telling you about. And okay, maybe this one. Okay, so if you take a look at this one, class, in your PACF, you can find here a significant spike here at lag 1 and significant spike. Maybe this is lag 3. Okay, so the PACF shows significant spikes, and then the ACF shows a an exponential decay. You can see this one, class. It's going down, okay, like this. It's showing an exponential decay. So this type of a PACF and an ACF is indicative of an AR process. You have significant spike at the PACF plot, and then an exponential decay, okay, at the ACF plot. Now, if it was reversed, if this was your ACF, okay, because ACF determines if it's an MA process, and then your and then your so let's suppose this is your ACF and this is your PACF. So your ACF shows significant spikes at some lags, and then your PACF shows an exponential decay. Then that could mean, class, that this is an MA process, because in the MA process you'll see significant spikes at the ACF and an exponential decay in the PACF, and the reverse is true for the AR process. If both ACF and PACF show this type of behavior, then most probably it will be an ARMA process, an ARMA process. Okay. However, if both of them show something like this, class, slow decay, for example, this one is a slow decay, class. See, it's not an exponential decay. An exponential decay goes down quite fast. Okay, it's not delayed like this. If it's like this, class, then that could be indicative that it is not stationary. Okay, that's indicating that your data is not stationary. We'll have an example of that. Okay, so good thing, class, good thing. We don't have to visually and manually try to generate a model from the PACF and the ACF. But that's how the softwares come up with the models. Okay, so like this one, class, let's take a look at this one. This is significant spike. Okay, so this is lag 1, okay, a lag 0. So this is 1. So we're not concerned about this. This will be really 1 because it's the correlation of the time series with itself. This is 0.4 and it's significant here. So significant spike at lag 1, okay, and then no more significant spikes. So this is indicative that this could be an MA1 process. Okay, if you take a look at the PACF, you see an exponential decay. Only the signs are changing, but this is an exponential decay. Okay, it's quickly decaying over time. Okay, all right. So this is indicative that this is an MA process. And once again, if this was reversed, okay, that would be an AR process. And on the other hand, if both ACF and the PACF displays something like this, significant spikes at certain lags and then no more, then that could mean that this is an ARMA process, okay? An autoregressive and an MA component, okay? So maybe, let me see. I'll click this and There are, of course, several sites that you can visit, but let me just share. I hope I can get this is cross-validated. So maybe um, here are some discussions here. Okay, anyway, I'll just drop this, Control C, and in case you're interested, Control B. Okay, all right. You may want to let me also get this, Control C, and copy this here as an example of. Okay, Control B. Sample ACF and PACF plots. All right. So what we did last time was we generated our ACF and PACF. Okay. If we run this class, we now have our okay. Take a look at this. You have here uh, significant spikes at logs. You seem to have here a significant spike at log 1, and then also at log way 2, 3, 4, 5, log 5, okay, log 6, log 7. Okay. And then here we have a significant spike here at log 1. And then also significant spikes at larger logs. Okay, so by just looking at this, you might be tempted to say this looks like an exponential decay. However, it does not seem to be. There seems to be some significant lags, significant spikes at longer lags. So if you take a look at the PACF, this seems to indicate that this is a perhaps an AR process. You have significant spikes here. And this one, there is a significant spike here also, but very, very small. And the others are also very small. So if I would guess initially, I would bet on this, okay? So it might be an an AR process because you're looking at the significant spikes at the PACF, okay? Or it could also be an MA process too, an Arima process, Arima 1.1. And what is being done is that you have to look at the AR process, compute it, and compute for the AIC, and then also compute for the MA, and compare. Compare the different models, and what will be the basis of choice? The model that shows the lower AIC, Akaike Information Criterion, will be the model of choice. So that will be the basis for selecting among the different potential models, AR1, MA1, ARMA 1.1, etc. Okay. So we said here, okay. Okay. Now, so we computed for the ACF, right? Now, can you get the values of this one? The ACF and the PACF? Yes, we can. Okay. R can give that to us. So for this one, okay, I'll let you copy this code. I'm creating an object called ACF result. And it's simply the autocorrelation function of your Apple log returns. And then we're not going to plot it. Okay, so that it will not, if I remove class, the plot is equal to false. So let me do this first. And then comment this out. If I run this, okay, it will automatically plot your ACF here. Okay, so you seem to have, although this is barely significant, okay, and these are longer in the longer lags class. So normally this could longer lags like this class is usually is not the best way to model, okay, because this might mean AR6, or AR7. And usually it's not a good idea to really go into a model with longer lags, okay, unless there's seasonality, okay. But usually an Arima process can uh, an Arima process uh, can model log returns of time series uh, using just simple or just lower lags, and not necessarily higher lags like this. Okay. So what I did here was Control Z. Okay. I'm including this. It's 1, 2, 1. Okay, I need here. Is this correct? ACF. Oh, wait, sorry. Not this one and not this one. Okay. ACF, and then I'm going to run this. Control Enter. Okay, so now we have this ACF result. Okay, so it's a list of 6. So we can print it. Okay, if I click this class, ACF result. So this is a list. So it contains the values of your ACF. Okay, so you can access this ACF contains the values of our ACF. So we can run this code. ACF result $ACF. You know what this means, class, right? We're accessing ACF, and let's just run. Of course, if I use 1 to 5 or 1 to 6, log 1 plus will be okay. The one here will be the log 0, so it will contain the value 1. So I'm going to print this. Okay, here you go. You have the one here. If you recall, class, this is the correlation of the time series with itself. This is log 0. This is log 1, log 2, log 3, log 4, log 5. Okay, so we can get the correlations. Okay, all right. Let me pause for a while. Any questions about this? About getting the correlations?
Sir.
Yes.
Sir, could we write that down? Kasi wala yata sa file
Yeah.
na
You write this down.
yes po, sir. Thank
Yeah,
you.
that's why I deliberately did not give this to you, because I want you to write it down. So you have to write down, class. Anything that's not in the file, I deliberately omit it so that you write it, class. Okay, so please copy this. I'm going to give you time. Okay, and when you're done, class, kindly chat in the chat box. We wanted to see what were the first autocorrelations. Correlation of the time series with log 1, correlation of the time series with log 2, okay, etc. Okay, thank you, Kate. Let's wait for the others. Okay, these are the values now of your correlation. So the correlation of your time series with its log 1 is negative 0.06. Log 2 is negative 0.006. Log 3 is 0.02, etc. So you can see here that this is quite small. That's why the plot, when we plotted it, it was barely below 0.05. Log 2 is also very small. Log 3, log 4. So if I plot here, class. 1, 2, 3, 4, 5, 6, 7. Lag 7 and 7, 8, 9 are larger. So if I increase this, maybe I'll make this up to 10. Okay. And if I print this, you can see now that the the seventh lag 0.08, the eighth lag 0.07, and the ninth lag 0.09 are higher. And that can be shown here, class, in the plots here. Here. These are the correlations, class. And the seventh, eighth, ninth are higher than the first, second, third, etc. All right. May I have your confirmation, class, please, if you got it? Okay, good. Okay, let's give your classmates a few more seconds before we proceed. All right. Okay. So not only, class, not only the ACF, you can also do the PACF. So you can just copy this and then replace it by PACF. Ganun lang yung class. Same thing. Copy the one above and then replace it with PACF. And here we can also increase it from 1 to 10 maybe. Let's see the plots of your PACF. Notice that for your PACF, this lag 1, 2, 3, 4, 5, 6, lag 7, 8, and 9. They seem to be, they have higher partial correlations. Okay, so you have this big spikes, and you can see that here when we run this. Okay, so we again create this object PSA PACF results, okay, using the PACF function, and then let's print this one. Wait, let me first run this. Control Enter, and then let me see PACF result. So it's also called ACF. Okay, the partial autocorrelation is also called ACF. That's why I use this one. Okay, PACF result $ACF. And let's make it also 1 to 10. If we run this, Control Enter, okay, you can see here that this is Z, this is AC1, right? Should be the same. And then first, second, third, fourth, fifth, sixth, see, seventh is also high, 0.08, 0.06, 0.08. Okay, so this really validates the plot of the PACF here. You can see here that the correlations are higher at these lags and lower at the others. 0.08, 0.07, 0.09. I'm sorry, here. 0.08, 0.06, 0.08. Okay, once again, class, may I seek your feedback if we're okay so far? So not only can you plot the PACF, you can print the values. You can see if the correlations are strong with the time series and its log. You can see there also that the correlations are not that strong. Okay. For the first one, it's only 0.06. Uh, it's quite weak. Okay, good. Now, I just want to be clarified, class, because I just want to clarify what our discussion last time, because I said that in order to compute for ACF, you just get the time series and then get its lag one, for example, and then get the correlation. Then get lag two, compare and the original time series, and then get the correlation. Same thing for lag three. So that's the way to compute for your autocorrelation. However, I said that for the partial autocorrelation, you just subtract the ACF. Okay, let me clarify that you're not actually subtracting the intervening ACF autocorrelation. What you're subtracting is the effect of the autocorrelations on the relationship between your original time series and your lag. So the best way to do this, somebody asked me about this. So let's let's show this visually in Excel. Okay, so please install this package, open XLSX. Okay, make sure that it's loaded here. Packages. Once you have installed it, make sure open XLSX. Okay, make sure it's loaded, make sure it's clicked. Okay. So what's this for? It's used to read, write, and edit Excel files. Okay, once you're done, class, kindly chat, please. If you have loaded open XLX. We're going to do something, and you can do this if you want to write. Okay, thank you. Okay. Okay. Now, take a look at this code, which of course you will have to write on your own. Okay. So it's a simple code, class. Okay. So we have the data Apple log returns. Okay. I'm sure you have that, class. Apple log returns. If I view this, this is our Apple log returns, right? No NAs. Now what I can do is I can copy this to Excel, this file itself. Okay, so how do we do that? So any file that you have, an RMD file, you can copy it also. If it's like a spreadsheet, then you can use this OpenXLX file. So this is coming from OpenXLSX. Okay, that's from this package, which is not part of Tidyverse, so you'll have to really install it. Then we can use the function write.xlsx, and then we can state that it should be a data frame, okay, because it can't be an XS object, as that data.frame, and then Apple log returns. Okay, am I missing here something? And then comma. How would you want the file to be named? Okay, so you can name this, let's say, data.xlsx if you want the name, the Excel file to be named as such. Okay, so where will this be saved? This will be saved in your R project, in your working directory. So this makes it very convenient. Okay, so if you run this, class, okay, run this and open your R project. Okay, try to see if you have now this data, this Excel file, Apple log returns. Okay, so I'm just illustrating to you, just to clarify, because somebody asked about the computation for the PACF, which is good. Okay, I'm glad that the person was interested in really determining how the ACF, class, we're going to illustrate also, but let's use Excel because it's easier to visualize here in Excel. Okay, do you have this now, class? If you check your project, okay, you should see this now. So I'm inside my R project and I have this Apple _log _ returns. This is the result of the code that I run in R, okay, using write.xlsx from the Open XLXX package. Okay. So I'm going to please ask you to please write in the chat box if you were able to do so. If you were able to create a file, you can, of course, rename this the way you want. Okay. I just use the same name, Apple underscore log underscore returns, and then I specify that it should be an XLSX. Okay, good, good. So you should now have this class in your our project. You should now have this Apple log returns. Kindly open that class. Kindly open it and let's see. I'll delete this. Okay. You should have this. This is Apple log returns. Okay, the original name is Apple log returns, I think. Yeah. And I just made it Y sub T. This is our original time series. Okay, kindly please chat if you were able to follow along and if you were able to open your Excel file. So we just shift now, just for this purpose. We're just going to shift from R into Excel just to illustrate to you the ACF and the PACF because somebody asked me about it. Okay, and this is my answer to that. Okay, good. How about the others? Do you have the Excel file now? You may change the name here any way you want. I just named it Y sub T, make it simple. Okay, so this is from our Apple log returns. And there are how many observations? 2515 observations. Okay. All right, so this is our log returns. Now, what we can do is we will notice that these are numbers. Okay. So we create the Y sub T minus 1, Y sub T minus 1. Okay. If you recall, class, this is log 1. I'm going to copy, Control Shift down arrow. Okay. If you're using Mac, I think it's Command Shift, then down arrow. For Windows, it's Control Shift down arrow for it to go down. Don't scroll down because that can take long. And then I'm going to copy it, Control C. Okay, Control C. And then I'm going to go back, Control backspace for me to go back to the original site. And then I'm going to type it here. I'm going to paste here and then Control V. Okay, so I copied class. I copied the data. All right. So if I scroll down here, okay, I'll delete this class. Right? So if you check, the log 1 value of 0.007 is 0.13, 0.013. So this is it. So it's just as if I copied the whole number up and then copied it here. Okay, and if you check class, okay, why am I getting a 0 here? Maybe this is really a 0. So this is 0 returns. Okay. So it means that the price did not change. So this is okay. Okay. So it means that in this day, there were 0 returns. All right. So we'll do the same. Plus, we'll do the same. So this is now our Y sub T. Y sub T minus 1. Okay. And then once again, we do the same thing. Let's get Y sub T minus 2 and then Y sub T minus 3. So this will just illustrate to us how your ACF and your PACF values are computed. I'm going to copy here again, Control Shift down arrow, Control C, Control backspace, and then I'm going to copy it here. Y sub T minus 2, Control V. And then scroll down, and then I'm going to delete this two here. Okay. So if you check, log 2 is 0.0133, it should be here. And 0.031, it's here. Okay. So this is now my log 2. And of course, I'll be missing two values. Okay. And log 3, same thing, control shift down arrow, control C, control backspace to go here. And then I put it here, control V, okay, control down arrow, and I'll delete this three observations here. Okay, so this is our y sub t minus 1, y sub t minus 2, and y sub t minus 3. Okay, so okay, I'll give you a few seconds to see if you were able to to have this class. Okay, thank you, Christian. Okay, let's wait for the others. So I hope you have this one. Sam, thank you. Let's again wait for the others. And then we can now compute class for the correlation for the ACF and the PACF. I'll just inform you how to go about it. Okay, how about the others, please? Give your classmates a few more seconds. Okay. All right. I hope the others are able to follow. I'm only seeing a few responses. 1, 2, 3, 4, 5, 6, 7, 8. Only 8 students out of 18. How about the others, please? Okay. Okay, good. Thank you. Thank you. Okay, so let's proceed. So let's first compute for the ACF. Maybe let's put it here. ACF, autocorrelation function. And then let's get, if you want, we can get log 0. Okay, but log 1, log 2, log 3. Okay. All right, so for log 0, it will be just the correlation of the time series with itself. So in Excel, we can make use of the correl function. Correl, okay, so it tells us that it returns the correlation coefficient between two data sets, open parentheses. So you have two arrays. So for log 0, we go here, okay, and then control shift down arrow to scroll down, okay, and then control backspace to bring you back to the original place, and then comma. What is our RA2? Our RA2 is the same because this is log 0. Same thing, control shift down arrow, control backspace, and then close parentheses. There you go. So you're just getting the correlation of the time series with itself. Therefore, this will be a 1. Control enter. Okay, so it's a 1 as expected. And this is what we saw, class, in the plot, right? You have a line there that reaches up to 1, it means that it's the correlation of the time series with itself. So that's not of importance to us. Lag 1 is correlation also. But this time, it's the correlation of the time series with lag 1. This is lag 1 class. And when you get correlation, the number of observations should be the same. So we cannot correlate this one with this one. It should be equal. So for RE1, I'm going to start from here. Okay, I'm going to start from A3 so that it will be the same size as my lag 1. I cannot use A2. It will return an error term because my lag 1 does not have this value. Okay, so once again, control shift down arrow, control backspace to go back so that we don't have to keep on scrolling, comma. What will be our RA2? Our RA2 will be this one, our lag 1. Okay. Control shift down arrow, control backspace. Okay. For faster keyboard process, close parenthesis. Okay, and then control enter there. So you have negative 0.06, which is, we'll validate that later on. Okay. So this is now our autocorrelation for lag 1. Our autocorrelation for lag 2, same thing, correlation between this time, it's with lag 2. It's with this one. So I'll have to start with this one so that it will be the same number of observations as lag 2. So once again, from here, control shift down arrow. Okay. For Mac, is it shift and then control backspace to go back there so that I can type comma. And then I'm going to, for RA2, it will be my Y sub T minus 2. Control shift down arrow to go down. Control backspace to go back to the active cell and then close parenthesis. So there you go. So you notice that you have the same observations. Control enter. Okay, so you have negative 0.006. So the correlation between your time series and your lag 2 is really very small, practically 0. And lag 3 will be is equal to same thing, correlation. Once again, we start with this one class so that it has the same sample size as your Y sub T minus 3. So here, control shift down arrow, control backspace, comma, okay. And then for Y sub T minus 3 here, control shift down arrow, control backspace. So that we don't have to scroll down using the mouse because that will take long. Control, you have, okay, right. If we check this class, if we check this and compare it with our R, yeah, let's see. What was the value of our correlation? Let's copy this. Control C, let me see. I'm going to copy it in R, in Excel, I mean. Here. Oops, sorry. Control Z. Didn't copy. Okay, anyway. Here, 0.0659 is the first autocorrelation, lag 1, the same class. Can you please verify if we have the same autocorrelation for lag 1, lag 2, and lag 3 with the R computation? Okay, can you make the conclusion, class? Yes or no? I want to see your chat, class. If the autocorrelation measures are the same using Excel or using your R. We just wanted to illustrate how the autocorrelation and the partial autocorrelation is computed.
Sir, question.
Yes, sure. Go ahead.
Sir, how did you do lag 0 on it? Kasi NNA yung sa akin po.
Sige. Christian, kindly, I'll stop share. Kindly share your screen, please.
Sorry, sir. I'm using a different device actually.
Okay,
Using
okay.
two PCs at the same time.
It's okay, sige.
Pero
Okay, so
what I wrote po sa lag 0 is yung correlation ng ano po. yung AAPL close, tapos yung
Which one?
YT
Which
sub 1.
one?
Yung
This
lag
one?
zero, yes po. Yung lag
Ah,
zero, how did you get
this
the
one.
correlation?
This one lag zero. Okay. So we just got the correlation of your time series, this one, and your time series also, because there's no
Ah,
lag. It's a correlation of the time series with itself.
okay, sir.
Okay, so it's A2 up to 82516, and then same A2 up to 82516. Okay,
Okay na
Christian?
po.
All
Yes
right,
po.
good.
Okay na po, sir. Thank you.
Okay, thank you, Christian. Thank you. Other questions, please? Any other questions? Okay. All right. Now let's go to PACF. This is a more challenging class. PACF. Okay. I loosely I said it was just removing the ACFs. Actually, it's deeper than that. So we will go to PACF lag 1. Okay, and PACF lag 1 will be the same as ACF lag 1. Why? Because if you get the partial autocorrelation between the original time series and lag 1, okay, there are no intervening. Okay, there are no intervening lags. Okay, y sub t and y sub t minus 1. Is there an intervening lag between y sub t and y sub t minus 1? None. If we were getting the partial autocorrelation at lag 2, then there is an intervening lag, which is lag y sub t minus 1. So we will have to remove the effect, okay, of the impact of y sub t minus 1 on y sub t, which we're going to illustrate in a while. So this one, class, will be just the correlation. It's also getting correlation. Remember, this is partial autocorrelation between, for lag 1, so it should be your original time series, control shift down arrow, control backspace, comma, and then this one is lag 1, control shift arrow, control down, uh, control shift down arrow, control backspace to go back to your original, to your live cell, close parenthesis, and then control enter. So it will be exactly the same as your ACF for lag 1. Okay, now let's go to lag 2. So this is what's different. So in order to compute for the partial autocorrelation at lag 2, what we have to do is we will get the correlation between your lag 2 and, okay, and your original less the effect of the let's say that's the effect of lag 1. So you'll have to subtract something. It's the effect of lag 1 on your original time series. So how do we do this, class? So let me illustrate that. Let me put it here, class. PACF lag 1. Okay. All right. Who among you have used, sorry, this is lag 2. Who among you have used the regression function in Excel? Raise of hands, please. Yes or no? I need to know that, class. Yes, if you have used the regression function in Excel, or no, if you haven't. No, thank you, Kate. How about the others, please? Okay, good. Okay, so let's do this, class. Okay, so this is an opportunity to learn for everyone. What we're going to do is we're going to regress y sub t on y sub 1, y sub t minus 1. Okay, we will we will uh, we will see the effect of your series y sub t minus 1 on y sub t. Okay, and then we will compute for the residuals. Okay, we will compute for the the residual effect. Okay, which means that what y sub t minus 1 can't explain as far as y sub t is concerned. So that entails getting a regression and getting the residuals. So that can easily be done in, okay, let me Okay. Okay, uncollapse this here. Okay. So you go to data here, go to data, and then tell me, class, if you have this analysis and data analysis. Kindly chat yes, please, if you have that data and then data analysis. Do you have this? Go to this tab, data, and then see if you have here in the analysis uh, ribbon, class, if you have this data analysis. Kindly please chat yes or no. Okay, good. Waiting for the others, please. Okay, good. So everybody has it. Data, and then in this portion, analysis. Okay, a few more seconds. I'm not getting the response of others. 1, 2, 3, 4, 5, 6, 7. 7 only. Okay, 7 out of 18. Okay. All right. I hope everybody has it because you cannot solve for the PACF if you don't make use of this. All right. So what we're going to do is we're going to regress the original data on y sub t minus 1. Okay. Then you'll develop a regression model there, and then we get the residuals. Okay. And then get the correlation of the residuals with y sub t minus 2. So that's in effect removing the effect of your intervening lag. Okay. And then whatever is left of the effect of the intervention, we will correlate with our y sub 2 t minus 2 lag. Okay, so let's do that. Go to data analysis, and then here you have some data analytic tools. Okay, you have ANOVA, you have covariance, descriptive statistics. You also have here regression. So choose regression and then click OK. Okay, so let me remove this. Okay. All right. So this should be what you have now. So let's first take a look at the inputs that we need to do. Input Y range. So our Y will be our original data set. Okay. So what we'll be inputting is not from here, but from here. Okay. Because our X range will be Y sub t minus 1. So if we input here, there will be an error because Y sub t minus 1 does not have a corresponding value here. So again, in the same manner that we did correlation. So we start here, that will be our Y range, control, shift down arrow, okay, control backspace. Okay. So this brings us back to the tab here. Okay. And then our X range will be, click this one, and then from here, control shift down arrow, and then control backspace. Okay, so check if you have the same number of data, 32516, 32516. So that's okay. Now, the data that we highlighted do not have labels, so don't check this. And then where are we going to put it? Let's put the result here. So in your click output range, okay, and then click it here. I'm going to put it here in M3, okay, under PACF lag 2. So just make it organized. And then you have to click this class, residuals. Okay, so this is very important because we want to generate the residuals, which is what the model cannot, what y sub t minus 1 cannot model. Okay, and then, okay, I'll just put here control alt print screen, so that control alt print screen. Okay, and then I'll click OK. And you can see here a summary output of our regression. Okay, and you can see here also what's important for us is the residuals. So if you're familiar with regression, this is the effect of your y sub t minus 1 on your dependent variable, which is y sub t. And this is statistically significant, 0.0009. Okay, for those of you who are taking up applied regression. All right. So how do we now get the correlation? The partial autocorrelation will be equal to the correlation, okay? The correlation of what? The correlation of your y sub t minus 2, control shift down arrow, comma, okay, control backspace, and then comma. Now take note, what we're getting is the residuals, or what this regression is not able to explain. And you notice that our regression here, okay, starts with A and B3, but our y sub t minus 2 starts at 4. So when we get the residuals, okay, we'll be getting the residuals here. Okay, we have to start from the second one. Otherwise, you'll have an error because it will not be the same size. Okay, start from the second one, control shift down arrow, okay, control backspace, okay, and then close parentheses. So that's now our PACF at lag 2. Okay, I'll pause for a while and allow you to catch up. Maybe I'm going too fast.
Sir.
Yes.
Sir, sorry, I switched PC na po. Actually, I got lost lang po sa part ng data analysis. Where do you
Okay, sige.
find that?
Okay. Okay, Christian, sige. Okay,
Yes.
let me redo that process. Okay. So in your Excel, do you have, if you click data, do you have this data analysis?
Sir, I only have the solver lang po, but
No
walang-
solver. Okay, good. So if you don't have data analysis class, this is how you go about it. So go to file. So click this one, please, file, and then options. File, and then options, for those of you who don't have data analysis here. All right. And then go below here in this here, add-ins, please. Okay, do you see it, Christian?
Yes po.
Add-ins, click add-ins. Click this one. Okay, here. Sorry, here. Let's go here instead of this one. Manage Excel add-ins and then go. Let's go here. Go. All right. Then, in your case, your analysis tool pack is not checked. Am I right?
Yes po.
Yeah, you check that, please.
Okay.
Check it and then okay.
Okay, sir.
Okay. Once you do that, go back to data and this should appear already.
Yes, sir.
Did it?
Yes po.
Okay. So let me review this. I will delete this. Okay. Control shift down arrow. There. Delete. Okay. Anyway, the lines do not matter. Okay. I'm going to put here the result of the regression. All right. So once again, we go here. We want to compute for the regression between y sub t and y sub t minus 1. So how do you perform the regression here? So you go to data analysis. Okay. Under data analysis, you have regression. And then okay. All right. Then input range for Y, it will be your original data set. However, make sure that it has it's the same size as your Y sub T minus 1. That's why we started here. Okay, so for Y here, it's from, okay, it's from not this one, but rather this one. Okay, because that will pair now with your Y sub T minus 1. Control Shift down arrow, Control backspace to go back. Okay, and then here in my X, I should be going to B3. That partners with A3 here. Control Shift down arrow, Control backspace. So I'm now back here. Now what we highlighted does not have any labels, so we don't click this. And then let's put the output range into, I'm putting it here. I'm putting it here at M3. I want the result to be here. And then I have to click residuals so that Excel will also generate the error terms. Okay, and then if we press OK, okay, you'll have this. You'll have this result, and what's important for us is the residuals. This one. Okay, so to get the partial autocorrelation, we have here is equal to correlation between, okay, this is log2 between your data for log2, Control Shift down arrow, Control backspace, and then comma, and the residuals. Okay, we removed the effect of the intervening lags. The effect of the intervening lag is a regression on y sub t minus 1, which is this model. So we have to remove we have to correlate your lag 2 and your residuals. So we have to deduct one observation. Okay, so I'm starting from this one, Control Shift down arrow, Control backspace, and then close parentheses. So that will now be my correlation. Okay, and then Control Enter. All right. Can we please compare, class, the lag one? Okay, let's do this. Last example. So I'm just going to remove this. This is no longer needed. Delete. Okay, and I'm going to put here Control C, and then I'll put here Control V for lag 3. Okay, for lag 3. So this one, okay, same thing. We have to first create a regression. Okay, I'm going to data analysis, regression. Okay, okay. What is our y? Our y is our original time series. Okay. However, what will it be? Now, take note that for y sub lag 3, you'll have to remove the effect of y sub t minus 1 and y sub t minus 2. Okay. So we will have to regress on these two, y sub t minus 1 and y sub t minus 2. So I start with this one, Control Shift down arrow, Control backspace. And then for my x, I have two predictors, y sub t minus 1 and y sub t minus 2. So it should be this two. Okay, because we're going to remove the intervening effect of your intervening lags, which is y sub t minus 1 and y sub t minus 2. Highlight both, Control Shift down arrow, Control backspace. And there you go. It's B4 to C2516. This is A4 up to A2516. Same thing. The output range I'm going to put here. I'll put it here at U3. There. Same thing. Generate the residuals. Okay. And then, okay. Okay, so we now have our model here, our regression model, where we have y sub t minus 1 and y sub t minus 2. So we're removing the effect of y sub t minus 1, y sub t minus 2, means getting the residuals. Okay, so our correlation now, partial autocorrelation here, will be equal to correlation of log 3, which is this one, class. This one, Control Shift down arrow, Control backspace, comma, and then the residuals. But we have to remove one because when we computed the residuals, we started with 4, and this is already with 5. So in order to not to have an error term, okay, we're going to start here, Control Shift down arrow, Control backspace, and then there you go. Close parenthesis. So we're getting the correlation between log 3 and what was left. Okay. What was left of the impact of y sub t minus 1 and y sub t minus 2 on y sub t. Control Enter, class. Okay. So I have here minus 0.0. We just copy this, Control C, and let's compare it with our partial autocorrelation here. So this is our PACF. And just right here. Okay. So is it okay? There's a bit of small difference, class. Negative 1079. Negative 1079. Okay. So this is due to the rounding off. And negative 0223, negative 022. In this case, it's practically the same. 0224, 4 decimal places, 0224. Okay, there's a very, very small difference because, again, of the rounding off. Okay, so we were able to show, class, how to compute your partial autocorrelation and the autocorrelation is fine. It's very easy. The partial autocorrelation is more difficult. It's more involved. Okay, good thing we don't have to compute that. And again, what's the purpose of computing for the ACF and the PACF? ACF will tell you. So once you get this, then you can plot it. That's where you get your ACF plot. Once you get class your PACF, you plot it. That's where you get your PACF plot. Okay, and that's what you will be using in order to determine if it's an AR process or an MA process. But good thing, class, as I showed you last time, we don't have to do that. Okay, because we can now use this. Okay, so this was our what we discussed last time. So once again, if I run this, I'm creating AR1 model. I'm using the Arima function. What I'm modeling is the Apple log returns. Okay, and the order is 1, 0, 0. And then if I get the summary, I'm going to get this. So this is what we got last time. And we learned how to generate the equation for this one. So the equation for this one is, okay, this one. Okay. All right. So y sub t is equal to 0.009, okay, which is this one, class. 9e to the negative 4, that's 0.009, okay, plus negative 0.66 times y sub t minus 1. Your y sub t is your Apple log returns, okay? I just denoted it by y sub t. Of course, you can replace this with Apple log returns, okay, plus your epsilon sub t, where y sub t is the current value of your log returns, mu is your intercept, this is your mu, and phi is your AR1 coefficient. Epsilon is your error term, epsilon sub t. Okay? Would you want this, class? Would you want this LaTeX? No? Okay. Not? Okay, sige. Let's move on, class. Let's go here. Okay, this was the second one. Test MA1 class. Arima, and then this is how you define your MA, 001. And if you run this, you'll have this, class. You have your MA1 component, negative 0.067, and then same thing with your intercept. So if you write the equation for this one, it will be this one. Y sub t is equal to 0.009 plus negative 0.675 times, notice now, it's now not y sub t minus 1, but epsilon t minus 1, plus your error term. So this is the difference between your MA and your AR. Your AR makes use of your past log values of itself. Your MA will makes use of your past error terms. Okay, and then here, class, for your ARMA 11, you have your AR component, you have your MA component. Okay, so if I show this in equation, same, this is your intercept plus the coefficient of your AR component, and then the coefficient of your MA component plus your error term. Okay, so this is your mu, this is your phi sub 1, this is your theta sub 1, your error term. Okay, here. Okay, I hope you did this class. You were supposed to do this. I was supposed to collect it, but I decided otherwise. And then here, okay, AR 21. So you have here 201. And how will your equation look like? Now notice there are some warnings here. NANs produced. Okay, so I'll explain what this NANs are. But let me first, this is your AR component. This is your AR2. This is your MA1. So the equation should look like this. Okay, here, class. This is your intercept. This is your coefficient of your AR1, coefficient of your AR2. This is your MA1 plus a certain error term. Okay. And you have NANs here. Let me see if I can. I hope this. Let me see if this will. Control C. It's almost time. I'm sorry. Okay. Control B. Okay, there. Kindly. Oops, sorry. This is a problem with sending message in Zoom. It's so stingy. Delete. Okay, here. Okay, so that's the first part, and this is the second part. Control C. Control V. Okay, so please copy that to explain what those NANs mean. Okay, it means that there's something wrong with the model. And usually that will happen, class, if you have higher lags of higher lags. Okay, so let me just end here, class. I hope you don't mind me. This, by the way, is the difference here, class. 111. So if I show you the equation, okay, the series will no longer be y sub t. Your series will now be your delta y sub t. So this is your difference series now, and it's denoted by delta. Okay, so the same thing, constant plus phi1 delta y sub t minus 1 plus your error term. Okay, so what changed now is that you're not modeling anymore your original time series, but your difference time series because of the one here, class. So take note, you're now modeling a different time series. Okay, so I hope, class, that you did everything here. Okay, so let me just share this with you, and let's run this. Run this too, and we'll end here. Control C. So kindly copy this, class. I'm sorry for a little bit of extension. Okay, Control D. Yeah, because how do you know which is now the best model? Good thing, class, there's this auto.arima. So here, this function comes from the forecast package, and I'm using auto.arima, Apple log returns, and then I'm creating the best model. So which among the models, class, is the best model? If I run this, best model, class, then it will tell us that the best model is an Arima 100. That's the first one, this one, class. And what was the basis? It was based on the Akaike information criterion. It has the lowest Akaike information criterion. And if you want to trace to see what were the models used, we can maybe call this best model 1, best model 1. Okay, we can include this trace is equal to true. Okay, so let's see what happens with trace is equal to true, which was not run in the previous code. Run this. Okay, take a look at this. R now comes up with several with many types of model. And then it chooses among the lowest AIC. So it turns out that the lowest AIC here is this one. Okay, this one, it's negative, so biggest negative class. The lowest Akaike information criterion is Arima 100. So it now recalculates and tells us that the best model is an Arima 100, okay, with non-zero mean, which means there's a mean there, and these are the coefficients. Okay. All right. So this is a very powerful function class, auto.arima, and then trace is equal to true. It will we will not have to manually look at each model one by one. We just have to use the auto.arima. Okay. So it's time. I'm sorry to extend a bit. Let me stop recording.